So today, uh, me and Kishore would like to give an update on a vector API, the project which has been part of Project Panama for quite a while. So I'm employed by Oracle, so there is a bonus slide on the slide deck I have to present. And since it's a joint talk, Kishore his own slide from Intel as well. So why do we care about vectors? So, since the Moore law is still holding, there are problems with performance starting to start a couple of decades ago, early 2000. There were no improvement on raw performance on per core basis, and that was related to the hitting the power wall. So people started looking into parallelizing their workloads to get along with the with the performance. Still, the transistor count continues to grow, and there are multiple levels where you can benefit from that. On a machine level, spanning across multiple hosts. On a single CPU level, there are many core systems available these days. And on a core level, there are SIMD extensions, which allows to process many elements at once. So along with the CPUs, there are specialized hardware available these days, like GPUs, FPGAs, different ASICs. But for today, we focus on CPUs. What can be done with CPUs? And looking at what happens with the CPUs these days, it's not uncommon to have systems with tens of hardware cores available, and like the top tier Intel Xeon has up to 56 cores, and there are 2 threads per core. So if we look at such a CPU, we can see that if you're able to utilize AVX512, you can get like up to 2,000 elements at once on a CPU level. So how does SIMD looks on a hardware level? There are wide multi-board registers available. Like right now, on a recent x86 systems, there are 3 sizes of register available: 128, 256, and 512. And those represent like a sort of packed vectors. And instructions operate on vector registers, treating the individual parts depending on the instruction. Like the same register can be interpreted like a vector of integers, vector of doubles, vector of shorts. So the instructions are able to gather values from memory, where they are laid densely in memory, and operate on them and then store them back. So today, all modern architectures provide different levels of SIMD. Like on x86, there is a multitude of different extensions available. ARM has Neon, and they have been talking about SV and recently announced SV2, and Power has Ultivec for quite a while. And it's not something like established, like it evolves quickly, and like during recent years, like starting since 2017, AVX512 was extended with numerous small extensions. Like every new architecture from Intel adds some new smaller extensions to AVX512. So AVX512 is not something monolithic, but there are multiple smaller extensions incorporated into it. So it's very fragmented at the moment. So what are the options to use those instructions in your workload? So you can split them in 3 different categories, like automatic, when the platform does it for you, and sequential semantics of the language and code patterns gets into the way, so it's easy to break it. You can annotate your code with some pragmas and get it, get some, provide some help to the platform, but it requires manual work. And you can code explicitly, like exercising individual instructions, trying to get the benefit. So JVM in a good position in that respect because Java bytecode is inherently platform agnostic. So for platform, it's easier to exercise individual extensions available at runtime because using CPU probing. Like depending on what hardware you run on, you exercise some particular instructions. And the dynamic code generation helps here as well. Use only instructions which are available. So right now, Hotspot provides automatic vectorization in C2 compiler. And some JVM intrinsics utilize vector instructions as well. But there are some problems, like, as I mentioned, automatic vectorization is brittle. So tiny changes in the code, which looks benign, can easily break the optimization. So the optimization is inherently conservative. Intrinsics are powerful, but they are point fixes. You can only intrinsify some particular operations available on the platform API. So it's not a general solution. You can't vectorize your own code using intrinsics. And if you can definitely use GNI, but the overhead is quite large, and VM doesn't have a representation for vector values. They are not part of JVM type systems, so you have to use some workarounds which are hard to optimize. So that's why we care about explicit API for vectors, and it looks like it's time to embrace the explicit vectorization on the JVM. And sure.
Yeah, thanks, Vladimir. So here are the goals which we set out for Vector API. So the first goal is the API should be expressive and portable. So expressive, by that we mean is our API should be able to express all the common vector operations which are available on different hardwares. So there shouldn't be any missing API because of which would hinder users from using the API. And portable API follows the Java programming model of having a portable API. The second is performant. So whenever there is a hardware support for a particular instruction, our API should guarantee that the compiler would actually generate the right vector instructions and use them. The third one is graceful performance degradation. What this means is if you run your vector API on a platform which does not support that particular instruction or that particular vector length, the performance shouldn't degrade as much as compared to the scalar version. So those are the three goals which we keep in mind when we implement Vector API. So let's start with some basic definitions. So what's a vector? So we define vector as a tuple of scalars of a fixed length of V length. Scalars are all of the same type, which we call E type. And these scalars which are currently supported in Vector API are byte, short, int, float, and the float long, and the floating point types float and double. V shape is the total size of the vector, which is the product of the length and the number of bits in a given type. And V shape determines how the vector is mapped to the underlying hardware. Each location, we refer to each location in the vector as a lane. So in this example, we have a vector of length 8. And so when we refer to the first element in the first scale in the vector, we call it the lane 0, and lane 1, and so on. So what's inside a vector? So as I said before, a vector shape, a vector of a particular shape, like in this case, a 128-bit vector, it gets mapped to a hardware instruction like XMM on Intel platforms. And depending on what kind of vector it is, it could pack 4 integers or 4 floating points, or it could pack 2 longs or 2 doubles. Similarly, it could pack 8 shots. So to represent vectors, this is the class hierarchy which we define. So the top level of the hierarchy is the vector class, which is parameterized by the element type E. And so this class implements all the operations which are common across all the vector types. Further down, we have classes which are specific to a particular type of vector. So for all the integral vectors, we have byte vector, short vector, int vector, and long vector, and we have float and double vectors. So this classes define methods which are specific to a particular type of vector. So for example, all the integral vectors would define operations such as bitwise bit manipulation instructions, which are not available for floating point. Floating point vectors would, on the other hand, would implement methods like exponential, like sine, cos, and so on, which are only defined for float vectors. They also override the methods which are defined in the vector by having specialized parameters. And below them are the concrete vectors, which are concrete vector classes, which are defined for a particular type and particular shape of a vector. All these vectors are private. They are not accessible to the user. So, but all the instances of vectors are instances of all the concrete classes. So users typically get access to vectors by factory methods on the top two classes. So along with the vector classes, we define different auxiliary classes to help in our computation, one of which is vector species. So vector species is a class which helps us to manage all the vectors which are of a particular type and a particular shape. And these are most commonly used when you first create, when you actually create vectors or even you load vectors from memory. There are certain fixed instances of species which are defined for each available type and shape. And these are accessible via the constant fields defined in the typed vectors like int vector dot species 512. So this species 512 would represent all the vectors of shape 512 bits and which have integer values within them. Similarly, you could query the vector species class to give you a particular vector species of a type and of a particular shape. The species method on a vector gives you the species which the vector belongs to. And so which are operations which you define on vectors, they should be applied on the vectors of the same species. For example, if you invoke a method add on a vector v1 and pass it v2, so both v1 and v2 should have the same species, else a runtime exception would be thrown. And even the result returned by this addition would be of the same species as the two vectors. So let's first look at how can we create vectors. So the most commonly used and the primary operation which we support is from array. So in this, I'm using int vector as an example. So from array is a method which you take the species as an input, as a first parameter, and the second parameter is the int array from which you want to load the vector. And the third int parameter is the offset into the array. And it would return a vector of the given species. Similarly, there are other methods which for creating vectors. So from byte array would load vectors from an array, but instead of int arrays, it would load from byte arrays, and it takes an optional byte order. There are many methods which come in handy when you are creating vectors, such as you could create a vector from values which you pass directly to the function. You could broadcast a single int element into an integer vector. Similarly, the single method would give you a vector which just has one element at lane 0, which is set to the input parameter. So there is a random method which would return you an int vector of random values. And along with these operations, the other way of creating vectors is by operating on vectors. So vectors are immutable classes. So whichever operation we do on vectors would return you a new vector. So with this, let's take a example, a simple example. Suppose you want to multiply two arrays, float arrays. The scalar way of doing it is um, you iterate over the elements of the array one by one. And if for each element you multiply the corresponding element in the second array and store the result um, in the result array. In vector API, you could do the same thing where you first start with the species. So first you fetch the species which you want to work with. So in this case, you're using float vector dot species 256, which is on Intel hardware, it would map to AVX2 registers. So in the loop body, you would create a float vector AV from the first vector by passing it the species and passing the offset into from which you want to load the array from. Similarly, you create the second vector from the input array B. The then you multiply the two vectors using the mul operation, and that will return your float vector CV. And finally, you store the vector into the result array. And if you look at the loop controls, here you, instead of striding over one element at a time, you would stride over a species.length element at a time. So in this case, since we are using 256, you would stride over 8 elements at a time. So in this code, if you notice, we have conveniently assumed that the input vectors are a multiple of the species length, which might not be the case typically. So this is how you would code for arbitrary array length. So similar to the earlier example, you have the main loop, which would iterate over the arrays in strides of the species length. And at the end, you had to write a tail loop in which you would go through the arrays one by one to process the tail elements. Here, the difference in the terminating condition of the loop is, instead of using array.length, you have to compute the right size at which you have to stop. So if you don't, if you read, if your array is not a multiple of species length, and if you read past the length of the array, then you would get a array index out of bounds exception. So, to help you with the computation, there is a helper method called loopbound, which on a defined on species, which takes the array length and it returns you the largest multiple of species length, which is less than the length of the array. So this is yeah. So one problem with this is not only you had to repeat the computation in the main loop and also in the tail loop, but also you have to the main computation happens in the vector API using the vector API semantics, and the tail loop you're using the regular Java operations. So this could lead to problems about error-prone code. So to solve that, one way to solve it is using mask. So I'll talk about mask later, but for this example, in the tail processing, we are using create a mask. So mask is basically a sequence of true and false values, and a mask can be used in vector operations to select whether you have to operate on a particular lane or not. So in this example, you create a mask using a helper method index in range defined in species. So depending on your array length, the first few elements of the mask would be true, and the later elements would be false. And you use mask when you're reading from the array. So use the same API as in the main loop, but you pass in the mask. So the A vector which we loaded in the tail, it would only load the first few elements from the array, so that it won't read past the array length. And the rest of the elements would be the default value. So in case of integer, it would be 1 or 0. Yeah. So similarly, you load the second array and you use the same computation in the tail loop. So at least we have the same computation. So this is less error prone. Even better is you don't have to write a tail loop. So you could use the mask in the main loop body to start with. So here, in the body of the main loop, you start with creating a mask. So using the current index and the array length, you create a mask, and then you use that mask to load from the array. And then after you do the computation, you write using the mask again. So what that means is the first, except for the last iteration, the mask generated would be all true. So only in the last iteration, when you are at the end of the array, that's when mask would have first few elements as true and the rest element as false. So we still don't have, we don't generate optimal code for this kind of situation. So, but in the future we will work on optimizing such kind of computation, such kind of mass usage. So right now it's not recommended to use such kind of loops. Oops. So in the earlier examples, if you remember, we used species 256. So we had hard-coded to use species of length 256. And that code would work on AVX, like a Intel AVX2 machine or Intel AVX 512 machine, but it would give a good performance when you're leaving some performance on the table when you're using 256-bit vector on a 512-bit machine. Or if you go to a machine which just supports 128-bit vectors, the earlier code won't generate the optimal code. Uh, won't be as optimal. So what we recommend is writing species agnostic code. So for that, we provide a special species which is called species preferred, and this species preferred is uh, um, initialized by the class loading during the class loading time to have to carry the species the which is the maximum length of the vector which is supported by the underlying hardware. So so this run so in this case we use a species which is preferred for the current platform, and the rest of the computation is the same. So since we are striding over species length, so if the species is eight values is of length 8, you would stride over length 8. If it's 16, you would stride over 16 values. So we saw a glimpse of mask before. So here is a more detailed explanation of mask. So mask is an ordered immutable sequence of Boolean values. So it's similar to vector in many aspects. So it's also like a sequence of values, but only Boolean values. It has a species, it has a length. So it's similar to vectors, but has a different usage. So the operation which are supported on mask are different. So mask only supports logical operations like AND, XOR, and so on. Most operations except a mask. So there is an overloaded operation for every operation, which would take mask as input. And what that means is, if a mask is set at a particular lane, that operation gets applied to that lane elements. If it's false, the operation does not get applied to that particular lane. So masks are a way for us, gives us a way to express control flow in the vector API code. So here is an example how you could encode control flow using mask. So let's suppose you have an income array. And suppose for every income less than 1,000, you want to bump the income up by 20%. So the scalar way of writing this is fairly simple. Go through each element, do a comparison, and if it's less than 1,000, you apply increment by that percentage. So in vector API, you could do the same thing using mask. So the as before, you start with the preferred species. Using the preferred species, you load a vector from the given float array. And then there is the comparison. So the float vector fv dot less than lt is less than. So there you do a less than comparison of every element in the vector with the value 1,000. And what that gives you is returns you as a mask. So the mask would be set for whichever lane values which are less than 1,000, and it would be unset for values which are greater than 1,000. And you could use that mask in your further computation. So you do the multiplication, and where you pass in the mask, and only where the mask is true, you would the value would be multiplied by there's addition step which I missed, I think. So yeah, it's multiplied by the given percentage, and you would add it to the vector. And finally, then you store the result vector into the income array. So this is how you could encode control flow. So following other different ways you could create mask. Like vectors, you could load mask from arrays. You could create it from values. There are some helper functions such as mask call, indexing range, which we saw earlier, which would help you create mask. And like we saw before, comparison test on vectors yields in a mask, and also operation on a mask, which will give you will return you a mask. Okay, now let's look at the different operations which are supported by vectors. So the primary classification which you use for the operations is lane-wise versus cross-lane operations. So on the left side, you see a lane-wise operation. So what that means is the add operation, which is passed to lane-wise, it gets applied to the corresponding lane in the participating vectors. So another way to think about it is the addition operation is um, broadcasted across the vectors, and the corresponding lanes in the two vectors participate in the addition, and you get the result in the corresponding lane. A cross-lane operation is an operation which is applied on the values in the same vector. So one example is reduce lanes. Here, to reduce, you pass a operation which is addition, and what it returns you a scalar value, which is the addition of all the vectors in the input vector. So here is a kind of an entire summary of the operations written in short form of available in Vector API. This slide and the next slide. So the first we had the binary operations, which are supported using the lane-wise method. So the lane-wise method takes a binary op and takes the second input vector and an optional mask. And the binary operation which we support are arithmetic operations, add, sub, mul, min, max. Then there is logical operations or XOR. We can do shifts on the lane values. Also floating point support, sine, cos, power of, and so on. Similarly, on the same lines, you have unary operation, which is again supported by lane-wise method, which takes a unary operation as the input and an optional mask. There are few ternary operations which we support right now. Example of which is FMA, where so a lane-wise method, an overload of a lane-wise method takes a ternary operation, and the two vectors which participate in the operation. Then we have comparison operations and test operations. So comparison is like we saw before, less than, equal to. They yield you a mask. Similarly, test operations to test the values within a particular vector. So we have a big a set of conversion operations, which I won't go into much detail, but I can just take one example. So if you look at, there's a conversion operation for integer to long. So what that does is it would convert a vector of particular species or of a particular type to a vector of different particular type or to a different type. And what conversion you want to apply to each lane is specified by passing any of these operands. So in the convert method, along with the operation, it takes the part. So this is for writing shape agnostic code. So what that means, let's say if you have a int vector of 512 bits, you're operating on int vector of 512 bits, and certain point you want to convert it to a vector of longs. So what that would mean is 512 bits would expand to a 1024 bit vector, which is not supported on the hardware. So to help you write shape agnostic code, you supply the part. So a conversion from integer to long would take two values for part, 0 or 1. So depending on, if you specify 0, what that means is if you expand 512 to 1024, you get the first half of the 512 into a 512 you'll get the first half of 512 bit vector into expanded into longs of 512. If you specify part number as 1, you would get upper half of the int vector into a resulting float vector. So we saw reduce lanes, which are the crosslane, which is one of the crosslane operation. Another one is rearrange. I will talk about rearrange in a while. So a few months back, we moved away from, so earlier we had methods defined for every type of operation, and along with that, each of these overloaded variants. So that resulted in like more than 140 operations which were defined and which need to be supported. So that's why a couple of months back, we moved to uh, expressing operation using lane-wise method. But still, we have some methods some operations which we call full service operations. So for those operations, examples of which are add, sub, mul. For those operations, we have named functions to perform those operations. So an add could be encoded using lane-wise and passing it to add, or you could directly call an add method on a vector. So the shuffles, um, if you were to define shuffles, ordered it's a ordered sequence of immutable int values, and what those int values are, they represent the source indexes when you apply a shuffle on a source vector. So basically, shuffle is an input to the rearrange operation. So when you do a rearrange on a vector, the int values in the shuffle uh, uh, determine from which lane you have to copy the values from. So here is an example where you apply a shuffle on the source vector, and based on the values, you get the result vector. Here's an example where, let's say you have an array of ints, and you have to add two consecutive elements in the array. So using shuffle, you could do it in this way. So start with the preferred species, and then you stride over twice the species length, and within the loop body, you first load I'm taking an example of 128-bit vectors. So first you load the first four integers into V1, then you load the second four integers into V2, and there is a convenience method defined in vector shuffle, which is called make unzip, which would return you the right number of which would return you a shuffle which you could use for such kind of rearrange operations. So it's basically unzipping. You pick alternate values from the vectors and put them together. That's what the unzip operation means. So here you get a shuffle. The first shuffle is for getting the even elements from the two vectors, and the second shuffle is for getting the odd elements. So on the right side, you have the example what's contained in the shuffle. So in the even shuffle, you have 0, 2, -4, and -2. So so it can have negative values. So what the negative values means is I'll talk about it in a minute. So after you get the two shuffles, you first apply a rearrange on the first vector, and also you first apply rearrange to extract out all the even elements uh, in the int vectors. So the rearrange is called on vector 1, and you pass vector 2 as a second input, and that would basically give you a vector which has 0, 2, 4, and 6. So with all the elements at even indexes in the array. And then a second rearrange using the shuffle created for extracting out the odd elements. You would apply rearrange using that shuffle, and that would give you 1, 3, 4, 5, and 7. So what we have now is the adjacent elements are now in different vectors, are like they are below each other. Now we could apply an addition on them, and then store the result into the result array. So yeah, here's an example of shuffle. So here are some examples of common vector computations, and I will show examples and quickly go through the generated code and the performance. So dot product is one of the first examples. So on the bottom is the vector version of dot product. So here we use FMA operation to operate on 8 float values at the same time, and you gather you use an accumulator and accumulate all the additions into an accumulator, and at the end you do a reduction on the sum to get the dot product of the entire array. So this is how the generated code looks like. So the compiler does unrolling. So inside you, it first unrolls it 4 times, and after that you see AVX2 instructions being used. This was generated on my laptop. So AVX2 instruction is used to load the 2 vectors, and uh, FMA operation is used for each of the 4 FMA operations. So you could get further more performance by unrolling the array. So one limitation of this implementation is each FMA operation uses the same destination register. So it creates a dependency from one instruction to the other. So you could avoid that by having 4 different accumulators. So unroll it manually, use 4 different accumulators, and then outside, once you are done with the main loop, you apply reduction on all the different accumulators and return the sum. So like before, this also generates 4 FMA instructions, but they use different YML registers as output. So this results in better use of the pipeline. Here's the performance what I see on AVX on Intel Xeon platform. So you get 14x performance with the first version, and roughly 16x performance, 17x performance with the unrolled version. Yeah, by the way, these examples are borrowed from Richard Statin's blog. So he's one of the earlier adopters of Vector API. This is another example from his blog where you could optimize matrix multiplication by working on tiles at a time, and also you could do unroll inside the loops. So you could work, and in this case, unroll 8 times to work on 8 different vectors. So the performance with this on a 256-bit machine, you would see roughly 3x performance, and on a 512-bit machine, you will see 5x performance. So vector APIs can also be used for the common JDK operations. So once vector API becomes part of the general JDK release, it could be used for example, for implementing hash code. So here, so this is the current implementation of hash code using scalar operations. So here's the process of how you could vectorize it. So if you think about unrolling the loop and working on different constants, so you can see you work on multiple powers of 31 on different values inside the array. So what you could do is you could convert these constants into a vector, pre-compute them, and then load multiply them into the input vector. So here's the vectorized version, how it looks like. So the main things to point out are you create the coefficient vector by pre-computing the powers of 31, and use that coefficient vector inside the loop, where you load 8 bytes at a time, or you load a vector, and from that and multiply that vector with the coefficient vector. Since we don't have much time, I would just skim through this implementation. There is another way of implementing vector hash code. So this is the same idea as dot product, where you use an accumulator. Instead of using reduction inside the main loop, you use an accumulator, and outside of the main loop, you do a reduction. And if you further unroll it, you get even more performance. So here's the performance which I see on a AVX machine, on a Xeon machine. So the first version of vector gives you 4x performance, and the last version which you saw using unrolling, it gives you around 12x performance. So along the same lines, array mismatch can be implemented using vector API. So right now we have an intrinsic implemented for array mismatch. But once we have vector API, we don't have to write intrinsics, because it's difficult to maintain intrinsics, and they need to be written at a lower level. So here's an implementation using vector API. Um, the thing to point out is using the compare operation to generate a mask, and and use the any true method. So if any of the values inside the mask are true, you break out of the loop, and then you do a scalar comparison. The performance we see with vector API is 2.5x with respect to the scalar version, an array mismatch, which is intrinsified, it gives you 3x performance. So this is one of the things where it either is a gap in the API or which we need to fix, or there are some operations which are better hard coded. So in this case, array mismatch generates a sequence of instructions which can't be easily generated by vector API. So this is one example of hard coding may give you better performance. So this is a final example of Sepia filter. Um, sorry, this is a scalar version where you apply the some computation on the different RGB values, and this is a vector version. And this is the generated code using vector multiplication and the blend operation. And this is the final demo of where so this is a pre-recorded demo of Sepia filter. This is running on a desktop. So this will give you a graphical representation of how vector API could be faster. So on the top is the vector API, which is already finished, and in the bottom is a scalar implementation. So you roughly see around 3x performance gain in this case. So I'll hand it over to Vladimir.
Thank you. So that's the API overview, and I would like to cover project status as well. So we have been talking about Vector API since 2016, and since then we went through at least 3 major rewrites on implementation level. There were 3 approaches, and we are like on a third run. So right now we are pretty confident we are close to release something into GDK, and the plan is to get it out as an incubator model. The API is deliberately non-final because we expect that future language change will significantly affect the API, like inline types, primitive specialization. With primitive specialization, we don't need, for example, to explicitly specialize code, like int vector, float vector should go away once primitive specialization is available. So on implementation level, the focus is on pre-AVX512 hardware. AVX512 is supported, but the implementation is not the most optimal one. And still, even if it's incubator module, the stability and quality requirements are high. So think of experimental GVM feature as an example of the quality requirement. So as of now, there is a gap in a candidate state, and the API. During past year, there was a major rewrite of the API. Kishore covered that, like lane-wise and all that stuff. It went in just half a year ago. So it's under official review. So once it's over, the plan is to get the JEP moving to propose to target and get it in an upcoming GDK release. So as I mentioned, it should be incubator project pending integration with the future language and VM features. So there are all the experiments going on with it, but we expect more adoption and more experiments once it's part of GDK release. So during past years, there was lots of work went into productizing the implementation. Right now, I would call it a feature complete state. So like all the functionality is there. There are still bugs which are being fixed, some inefficiencies. So, but the progress during past year was significant. So what to expect after the release? So there are still API challenges. So with the current state of the API, the operations and vector shapes look very nice. So they're mostly orthogonal, independent. So you can code in a way which abstracts away both the element types and vector shapes, but it's not applied to the data. Like you saw the loop shapes, like how you need to provide the post loop, tail loops, and that's what should be fixed with masks. as a stop the gap solution. And right now VM doesn't cover that fully, so it doesn't produce most optimal code shape, but it should be fixed in the near future. So JIT compiler should be able to lower that into efficient code akin to what auto-vectorization does, like spinning different loops most optimal to processing, like pre-loop, main loop, post-loop. And on an API, there are challenges like some people want to uh, care more about ease of use, but some people want to more access to hardware, and that's the plan for the future releases, like expand the API to cover both easier to use, so easier to code loop kernels, and closer to hardware, easier access to get to the individual instructions. So there will be a short talk tomorrow about code vectorization in the JVM tomorrow at 1 p.m. at the Groundbreaker Hub. So I invite all of you to go there and ask questions about the project, the API, and see you there. Thank you very much. So we run out of time. So unfortunately, there is no time for questions, but feel free to catch us right after the talk in the hallway, and we'll be happy to answer questions. And come join us tomorrow as well. Thank you.